Morning students, 5.4, and today we're continuing to practice integration by substitution, and we're going to look at definite integrals. So you'll see the question on the screen right now is a definite integral, and it's a substitution question. I'd like you to use the skills you've learned so far to have a go at it. I'll tell you the answer. The answer is 98, and I want you to see if you can get that. Pause the video, and when you're ready, we'll go through it. Okay, so we're going to look at two questions, just two questions today. So have a go at them, then write down the model solutions, and then really try and pick up the specific skills. First thing I wanted to say is when we do definite integrals, and we're switching to that dummy variable u, we're always trying to remember to do everything at once. So wherever we see an x, wherever anything refers to an x, we need to switch it out. And in terms of our question here, one thing we always have to switch out is the integrand, and that's the thing inside the limit. The other thing we have to switch out is the differential, so we have to switch dx, and that has to become du. So the differential here has to go. And then if it's a definite integral, the new thing that we have to switch out is the limits. Because when we do an integral and it's in terms of x, these values, 0 and 4, they are values for x. If we change the integration to be in terms of u, by changing the differential to du, then we must also change these values so that they are in terms of u. We're going to look at that now. So, in this first question, hopefully, building on the skills we've already got, you guys recognize that the tricky part of this is the x squared plus 9, because it's the power of half. So we're going to let u equal x squared plus 9. And obviously that deals with part of the integrand here. Looking at the differential, du by dx is 2x, which means that du equals 2x dx. And here's a clever thing, a trick for us. We have an x in front here. It's 3x, it's not 2x. But let's not worry about the constants. Remember, constants are always easy. If I put this x with the dx, then I can just swap that for du. And that means that with these two things, I can deal with the x squared plus 9 to the power of half, and I can deal with the 2x and the dx. So actually, and I guess this is the key thing, that the x here, I'm doing it in blue because it pairs with the dx. And we can do this substitution and to turn it to u, into terms of u. So as I look at this now, I'm able to transform the x squared plus 9. I'm able to transform the x and the dx. So the one last thing I need to do is I need to look at these limits. The way we do that is we just do a very simple table. We look at the values of x that we're interested in, which in this case is 0 and 4. And we just think, well, what is the value of u when x is 0 or 4? So we substitute in x equals 0. 0 squared plus 9 is 9. We substitute in x equals 4. 16 plus 9 is 25. And this information now, I'm trying to do the color coding to help you with, follow it through, means that now we're able to change everything we need to change, so the integral becomes 4 and 0 changes to 25 and 9, important to get them the right way round. I had a 3 and a 2. So if I substitute this in, the integral had a 3 in it, and I'm introducing a 2, so to cancel out with that I need to divide by it. It's 3 over 2. Have a think about that and work through those constants if that's not obvious to you. The square root of x squared plus 9 becomes u to the power a half, because it's x squared plus 9 is u, and the square root is to the power a half. And then the x dx we can switch out with du. And so our really tricky integration, through a clever substitution, has become an easy integration. What's super helpful about this is the coefficient now is exactly right for an easy integration, because u to the power 3 over 2 differentiates exactly to 3 over 2 u to the power a half, and we just need to evaluate that at 25 and at 9. When we have these fractional powers, the easiest way to think about that is it's 25 to the power a half cubed, take away 9 to the power a half cubed, so that is 5 cubed take away 3 cubed, so that is 125 take away 27, which gives us that answer I told you about, which is 98. Okay. You're going to get lots of time to practice questions like this in the exercise, and they come in slightly different forms. The new idea is this idea of switching out 3 things, and that's going to be the same in all these questions. Switch the limits, switch the differential, switch the integrand. Second question today I want you to have a look at. Apart from being an opportunity to use those 3 things, there are also 2 little tricks in this. First little trick is to split the cos cubed into cos times cos squared. And the second little trick is to actually use that first idea to change this integral into 2 separate integrals. I want you to have a think about that and have a go yourselves. Just like before, I'll tell you the answer. The answer is 2/3. See if you can figure it out. Come back to the video and I'll show you how to do it. Okay, so we have this question, and like I just explained to you at the outset, the first trick with one of these is to actually say, well, this is the same as cos x times cos squared x dx. It's worth me saying at the start, like, I can't just integrate this by substitution directly because it doesn't have that form where the derivative is in front. We know that the derivative of cos x is sin x, and it's just not there. So there's no workaround for that. There's nothing else we can do. We have to find a different way of writing it. So I write it times cos x times cos squared, and then I'm thinking, for my integration by substitution, I need a combination of cos and sine, because I need to have both a function and its derivative. And so what I'm going to do is I'm going to rewrite cos squared x as 1 minus sine squared, and that's actually going to allow me to split into 2 integrals here. The integral of cos x dx, that's cos x times 1, take away the integral of cos x sine squared x dx. And by doing this, I've switched to 2 integrals, both of which I know how to do. The first is a basic integral and simple. The second, whilst more complicated, fits the form for substitution. And so I'm going to evaluate these separately. So my trick for doing clear work is I'm going to say, okay, this is equal to I1 take away I2. So I'm defining the first integral as I1, and I'm defining the second integral as I2, and I'm going to work on them separately. I1. the integral of cos x integrates to sine x, and we are evaluating that at pi over 2 and 0. So it is sine of pi over 2 take away sine of 0, and so it is 1. So I1 is 1. Then we're going to look at I2. Let's have a look at it. 0 to pi over 2 cos x times sine squared x dx. Hopefully you've been doing enough of these now so that you can have confidence recognizing the substitution. The substitution is going to be u equals sine x. That allows me to look at the derivative du by dx, which is cos x, which the fastest way to do this is to say that du equals cos x dx. Because, go to my colours, cos x dx translates to this bit and this bit. Sine x, well, that allows me to substitute the sine squared x, and I can do the substitution here. But of course, there's always three things. I need to look at the limits. So, just like before, I draw a quick table. X and u. Two values of x are 0 and pi over 2. X is 0, sine of 0 is 1, so u is 1. If x is pi over 2, sorry, what am I talking about? Sine of 0 is 0. Sine of pi over 2 is 1. So my values are 0 and 1, which means I now have all the information I require to do the substitution. And my second integral, I2, integral between 0 and 1, must have them the right way round, of u squared du. And that complex integral we had before in terms of x has simplified drastically. We're on the home straight. We integrate that, we get a third u cubed between 1 and 0. We substitute in, and we get an answer of a third. So the overall integral I was I1 minus I2. So that is 1 minus a third. So that is 2/3. Okay. Really nice stuff. I want you just to take a moment to reflect on the fact that these are challenging techniques, and if you can follow this at this point, your calculus has improved so quickly over a really short period of time in challenging circumstances where we've been learning remotely. So feel really good about that. Obviously, you're going to have time to practice these questions and tell me what you've struggled with as you've gone through. I'm always here for you if you've got things you don't understand, so please do get in touch and let me know. Otherwise, best of luck, and I'll speak to you soon.